So we can resume for today. I remind you too, we have also a talk in the afternoon. So after lunch, you're not yet free. It will be 3 p.m. I think it's somewhere on the official schedule, but let's be sure it is. It's not on the printed one, it's on the electronic one. Anyway, so we start now at 11 with Yang Ma from Louvain with the Higgs-muon interaction, the multi-TeV muon collider. And I'll give you the time.
1 hour, right? Okay, thanks. Okay, thanks for the opportunity, and I feel quite enjoyable. I cannot say I'm excited anymore because it's been so long here. So, but it's quite enjoyable trip here in GGI. And today I'm going to talk about the Higgs-muon interactions at a multi-TeV muon collider. So basically, we are trying to look, to explore the way to measure the muon Yukawa. Here, so a bit warm up. Basically, I don't have to spend more time here because everyone knows that more than me. So in order to have a very high energy machine in the lepton sector, we are thinking about basically you have two ways to do that. One is linear collider to try to get rid of the synchrotron radiation. The other one is, okay, we follow the same logic that we built the Tevatron or LHC for the hadron colliders to look for the heavier beams. So we have less radiation for the loss, and we have a chance to really go to the TeV level to have a direct probe for the possible new physics. So this is the ring we are having in mind, and we have so many advantages over the traditional machines. Like we can have a smaller ring, we can save more electricity power for the same level of the integrated the luminosity, and yeah, the most important thing is another way to open the door to the TeV physics rather than I mean, I'm not saying it's gonna be better than FCCHH. I will never say that, but I've said that's another possibility. That's something different we can do. And here, allow me to review some old papers. This one is in 2020, written by Dario, Roberto, and Andrea Wuzer. They say, okay, there are two paths toward precision and at very high energy lepton collider. That I think they were referring to the muon collider. So basically, there are two kind of things and mechanisms are happening there. So one is mu plus, mu minus annihilation. The other one is VBF. Well, the annihilation brings us directly to the energy frontier, to probe TeV physics. And here I show two plots. I borrowed the two plots from the paper also in 2020 by Fabio's company in Louvain, like 4 years before I joined them. So they had a very rough comparison. This is for 2-to-1 process. This is for 2-to-2 process, and here is the machine energy for a possible proton machine. This is energy of a possible muon collider. And with a kind of a rough and naive and not so precise comparison, we draw the conclusion. It is process dependent conclusion that a 10 TeV muon collider, it might be comparable to a 7 TeV PP collider. So that means, okay, sure, it brings us to the energy frontier. It gives us a way to really probe the high energy physics there. And then I want to show another plot. Actually, this kind of distribution also appears in many in papers of other people. I think it also appears in the paper. Some of the authors also is sitting there, but I'm just quoting my own paper. Sorry for that. So this is an example for the TT bar production. This one is actually the VBF for the here is the TT bar inverse mass distribution. So you see the VBF, they peak at near the threshold, And then they scan the full spectrum, the energy spectrum. Well, the annihilation, they just peak near the machine energy that gives us a direct probe of TeV physics. Well, this one coming back here, this is the effect due to the ISR, initial state radiation, which is dominated by the QED case. That means you have one or more photon radiated out from the beam before the hard collision happens. That can lower the hard collision energy, so that you don't suffer that much from 1/s behavior. You have a bit higher cross section. So this is the kind of a general picture that you have. Okay, you want to go to high energy, you go to the annihilation. You want to go to the you want to generate some more Higgs, more top quark, whatever. You can think about the VBF channel, and also the VBF helps you to scan this spectrum. So for example, if we are not so lucky, assume you have a 14 TeV machine. However, the new physics particle is not 14 TeV, it's not around 14 TeV, so don't really go to the resonance peak. And also it's not at 7 TeV, so that you cannot produce them by pair. Maybe it's here. And then it is the VBF process that attacks here, approach here in the tails. That's what people always saying, like the new physics appears in the tails of the distributions. And allow me to also spend 1 more minute for this general picture again. This is the full picture. If we really think about the thing using the PDF way, the platonic approach, of course, I mean, when calculating this thing, for example, mu plus mu minus to Z Higgs and a pair of neutrinos. This is the VBF diagram. You can do that using the 2 to 4 full matrix element calculation. And you can also do that with the so-called effective W approximation by taking a cut here and here. You assume the WWs are the patterns. And you do believe that the unshelled W contribution is dominance, it's collinear splitting, and you can think about it in this way. However, I'm not gonna compare these two. I'm just telling you from this point of view what we see at the muon collider. So if you think about the pattern distribution thing, you can just like QCD. We can have this platonic luminosity, and we see, oh, this is for 30 TeV machine. So you have photon, or maybe photon Z, or the neutral current VBF as the pattern distribution. The luminosity here is the largest one, and then you have this mu plus mu minus annihilation, which peaks around 1. This is something like the valence quark in QCD point of view. This we can call that valence lepton annihilation collision. And we can also have the WW fusion. And here I separated different polarizations. So transverse W, longitudinal W. And we even have QQ bar or gluon, which is mainly from you have photons split it out from the muon. And if you continue the splitting using the degalactic evolution, you have a pair of quarks. You can have a pair of quarks after the photon. And then if you continue for the next order, you're going to have a chance to radiate out a gluon from the quark. So this is not really new, because that concept, that thing has been talked about long before we wrote the paper. People call that the resolved photon. So this is the picture we have. Okay. So this very high energy lepton collider, it has very clean background comparing to the hadron collider, but it still has a lot of patterns due to the radiation. And then right-hand side is like, okay, we can, if we do use the PDF thing, we can just do whatever the exactly similar thing as we have been doing in QCD. So if you are interested in only this Z Higgs production, we should use the sum overs mu plus mu minus to Z Higgs, and then also the different channels of fusions, WW fusion, photon collision, and the other things. Sorry, here is there's no photon. And here's the plot. This is the machine energy from I think 1 TeV to 30 TeV, and this dotted curve going down. For example, this blue one is for W pair production. This one going down is mu plus mu minus to W pair, which suffers from 1/S behavior. The higher machine energy you have, the higher suppression you have, even though you go to to probe the TeV physics directly. And then something going up with a logarithmic enhancement, this is a VBF. And in the very end, you say, oh, if you are only interested in this, for example, the Higgs production, in this thing, you say, okay, I don't see the missing energy. Obviously, you don't see the beam remnant. It's exactly the same pattern we were doing. We are familiar with in the QCD. So this is the so-called semi-inclusive cross sections. And then people say that the high energy muon collider is a Higgs factory because from this VBF, mainly it's dominated by WW fusion. You can produce if we assume like 10 inverse echo bar for the luminosity, we can produce 100 million single Higgs events and around 500,000 double Higgs events. Sorry, I put the triple Higgs production here also. So in this way, it gives us a chance to measure, for example, the Higgs self-coupling, to measure the lambda here. So if assume this is what we can measure at IHC, and this is if you continue increasing this luminosity, we can do things more precisely than IHC. And then if we do have a 10 TeV muon collider, we can do much better. So more details can be found in the the EPJC review paper towards a muon collider like 2 years ago already. And however, this is not what I'm going to talk about. What really matters is if we think about the multi-boson productions at the muon collider, which means WW production, or double Higgs production, or ZZ production, or Z Higgs production. Actually, I plot this. I made this plot just want to show that the VBF goes up and the annihilation goes down in the high energy region, and then we noticed, oh, there is a kind of gap. And if you zoom in, you see it's almost a factor of 2 at 30 TeV. So the difference is this solid curve, you have 2 ways to do the calculation. You either keep the muon as massless, and then you don't care about the muon you cover. You also set the Yukawa coupling to be 0, so you don't include the Higgs diagrams. Or you say, I want to be more complete. I keep the muon as massive, and then you need to include the Higgs diagrams. So both of these calculations can give you this solid curves, which is a correct cross section. However, if you did something wrong, say you assume the muon is massive because you want to deal with the radiation. You want to put this muon mass in the denominator of the log term, log Q divided by muon mass. And then you say, oh, the Yukawa coupling is so small, I don't really want to include the Higgs diagrams. And then actually you just broke kind of the gauge cancellation inside standard model. And then at very high energy, you see some unphysically large cross sections. And then we thought, okay, if that is the thing, we should go to higher multiplicity. So this right-hand side, we did, so here, yes, this is what we did. We set muon mass to be the muon mass in the standard model, but we set the Yukawa coupling to 0, which means there's no Higgs diagrams in the processes. And then you see here, something going up, the dashed curve is VBF. Let's put that aside. It could be our background. And something going down in the solid curve, that's the standard model, that's the correct cross-section. And something going up, kind of unphysical, gives you a very large cross-section in the high energy regime. You know, oh, we made a mistake because we did not do the correct way for the calculation. And then we realize If this is the case, that means all this multi-boson production, those cross sections, they're kind of very sensitive to this muon Yukawa. So then we say, okay, if we want to measure the muon Yukawa, we don't have to produce Higgs and look at the decay to muons. We can just look into these cross sections and say, if it's large, too much larger than standard model value, is the maybe from the BSM kind of like a Yukawa coupling. So that paper was written in 2021, and then we say if the VBF is the largest background that you are concerned about. So here is again the standard model. We kept this muon to be massive. We kept the standard model relation between the Yukawa coupling and this muon mass. But in the BSM case, we use kappa framework. So here, this is the inverse mass distribution, the inverse mass of the final state of the 3 bosons. This one is for WW Higgs. You see, okay, VBF goes this way, agrees with our expectation. It peaks in the threshold and scan the full spectrum, but goes down. And the other side is, this black curve is kappa equals to 0, which is the possible new physics. The kappa equals to 1 is the standard model. You see, they peak near the machine energy in this spectrum, but they are different from each other. So in this way, we can, and also we probe the angular distributions, which is the angle between the outcoming boson and the beam axis. And also we probe the angular distance between any pair of two bosons. So we learned, okay, we can put such kind of cut. And this inverse mass cut is mainly the game changer. So you see here, in this distribution, the solid curve for VBF is before cut, and this dashed curve for the blue one for the VBF is after this inverse mass cut. It's so much, orders of magnitude smaller than this one. So that allows us to focus on the difference between the black curves and also the red curve. The red one is the standard model as a background, and this one is the possible new physics. And then we thought, okay, kappa framework is something we play with like a toy model. We want to know better than that. So either we can go away. I mean, this is just the kappa framework. We introduced the kappa mu, and but if you go with the Higgs effective field theory formalism, this kappa mu is just the first coupling, first Yukawa coupling. And then they can introduce, you can actually introduce the Yukawa couplings for the mu plus mu minus to 1 Higgs, 2 Higgs, 3 Higgs, 4 Higgs, and so on in the Heft formalism. Or if we want to do that things in the linear representation in the SMAFT, we can also introduce the dimension 6, dimension 8, all the higher dimensional operators. So here, this one is for the Yukawa sector. This one is for the Higgs self-coupling sector. So we just parameterize them in 2 different ways. And in the very end, we realize that we can relate them together. So if we make things easier, kind of more transparent, more straightforward, we just introduce this alpha, which describes the n Higgs and mu plus mu minus vortex, and the beta, which is just n Higgs, the Higgs self-couplings. And then you see, this is a contact diagram. So mu plus mu minus to n Higgs looks like this, and the first one, alpha 1, is actually the kappa mu. And then we can write out this alpha 1, 2, 3, 4, 5 in terms of this dimension 6, dimension 8, dimension 10 SMAFT operators in the Wilson coefficients. And you see, alpha 1, alpha 2, alpha 3, if we believe that dimension 6 operator is really dominates the new physics effect, we can just remove them too. You remove the other things, you will see the alpha 1, 2, 3, they are linearly related to each other. That's the kind of strong assumption if we trust only the dimension 6 math. But this one, it doesn't exist in the Heft framework. So that's a new paper we wrote in 2023 around Christmas. And this is the processes we considered. So firstly, we can probe this one directly because it's just a number. So we can go from mu plus mu minus to 1 Higgs, 2 Higgs, 3 Higgs, 4 Higgs, 5 Higgs direct production directly to probe the alpha n, alpha 1, 2, 3, 4. And also we noticed if you have 1 Higgs, it can go to a pair of W plus, W minus, or ZZ. So that means in this count, 2 of the vector bosons means 1 Higgs. So we considered all of them in this color code, which means this one, 1, 2, 3, those ones, they depend only on alpha 1. Those ones, they depend on alpha 1 and alpha 2. Those ones, they depend on alpha 1, 2, 3. Those ones, they depend on alpha 1, 2, 3, 4, and this one depends on alpha 5. And we thought it's too much, maybe it's too much, so we should be, we should stop somewhere, so at 5. And the simplest case is we go back to revisit the Z-Higgs production that I showed before that we did in 2021. So at 3 TeV muon collider, this is alpha 1, kappa mu. So the cross-section is kind of flat. It's not so sensitive to this new physics. And the signal is slightly better if we do have a 10 TeV muon collider, because the BSM effect is really energy enhanced. And then we also have, as I said, 1 Higgs is equivalent to 2 vector bosons. So you have Z Higgs, you have triple Z, or WWZ. So we noticed that here, this triple Z is a kind of a better signal for rather than this Z Higgs. So we can try to measure, try to constrain the value of alpha 1. But you see, okay, it says from 1 to 0 to 2. The signal is not rather small, so we cannot really do any real precision test here. But there's one thing we can test. You see, if we do measure the Higgs to mu coupling, what we do, the most naive and straightforward way, intuitive way, is to produce Higgs and let it decay to see the branching ratio. And what we are doing is actually the square of this kappa mu, obviously the square of alpha 1. So you can only know how far away this new physics is from, this alpha 1 square equals 1. However, here we can see that the alpha 1 equals to -1 is quite different from alpha 1 equals to 1. That's because this process is also is kind of dominated by the gauge coupling diagrams. So there is some interference between this gauge coupling diagrams with those other diagrams with the Higgs diagrams. This is something we cannot do for Higgs decay to mu mu. And then we go to the golden channel. If we think about this thing to try to simplify, it's a little bit oversimplified. We try to simplify this thing in the high energy limit, and actually we can. That means we do ignore the mass of the Higgs. We ignore the mass of the vector bosons. We also ignore the mass of the muon. But sorry, we cannot ignore the mass of the muon because it appears together with alpha to show this. If alpha equals 1, this is alpha 1 equals 1. This is the muon Yukawa. You cannot really set a muon equals 0. But here is a plot for like mu mu to 2 Higgs, 3 Higgs, 4 Higgs, 5 Higgs, 6 Higgs, 7, 8, 9, 10 Higgs productions. And this is a cross section. And you see the blue curves are for the 10 TeV muon collider. The red curves is for the 3 TeV muon collider. And there's also, I put one additional curve for alpha n equals to 1% and at 30 TeV. Okay, for sure, this breaks, this hits the unitarity bound. So we can measure, I mean, we can do some constraint even before having this, this machine. And these two flat lines are for the limit where you see 3 events at a 3 TeV machine, or you see the 3 events at a 10 TeV machine with the corresponding luminosities. And the solid curve is for if you assume alpha n equals to 1 or 0.5 or 1%. So that means it's possible to measure this alpha n to around like 0.1 or even smaller at such a machine using those multi-Higgs productions. What? Sure. No. You mean the polarization of the beam? No, we didn't show this. We didn't do this polarization. I think it should be longitudinal. It should be longitudinal because that's high energy thing. And but however, we need to do some more realistic analysis rather than this high energy limit, because for example, if you produce 5 Higgs at a 3 TeV machine, the 5 Higgs, the sum over the mass is over 600 GeV. You cannot say that thing is massless at a 3 TeV machine. So we need to do some real, and also this one is noticed not only by us, also by Random Dharmasak's company when they were in Indiana. And then we did some more realistic analysis where we see the leading order of the standard model cross section is super small, not even 1 event. So here is double Higgs production at 3 TeV, 10 TeV, or 3 Higgs triple Higgs production at 3 TeV and 10 TeV. So here is the leading order. You see 10 to the minus 7 femtobar, 10 to the minus 8 femtobar. For higher energy, it's even more surprised because you have a very small, you have coupling, you don't want to go that. So this is basically negligible for the background. And then we notice that the loop-induced double Higgs production is large. So that is our background. So here is loop-induced double Higgs production at 3 TeV and also at 10 TeV. This one is at triple Higgs production, and this is 10 TeV also. And here's the VBF. As I said, after we applied those cuts, VBF gives, for example, here it's only 0.12, 0.12 in ones, which is negligible. And this loop-induced one gives you around 3 events, comparing to if you assume that alpha 2 equals to 1 is 23 event. That means this one is the main background. Also true for this thing. But however, if you go to higher multiplicity, here as I showed in the 3 Higgs production, even the loop-induced 3 Higgs production it's not able to give even 1 event for at 3 TeV machine with 1 inverse echobar luminosity or 10 TeV machine with 10 inverse echobar luminosity. And you see this new physics signal is super strong if you assume kind of order 1 of the alpha 2 or alpha 3 coupling. That tells us if you want to do like 4 Higgs or even more, you don't even need to bother yourself with the loop-induced calculation, which is good. And the only thing I need to say by that point, we wanted to show the physics potential of the future collider. So we didn't know the misidentification efficiency from from the J boson. So here is a little bit over optimistic, but I think it shows gives you some message. And then here is the result. This is for double Higgs production as a function of the alpha and also beta. So the beta, if you still remember, the beta is the parameter that describes the difference, in the Higgs self-coupling part. So that's beta 3 Higgs coupling. So here you're going to see, I think you also see some beta 4 for 4 Higgs coupling for 5 Higgs productions. A good thing is for almost all of them, they are not sensitive to the Higgs self-couplings. So that means, okay, we are allowed to focus in the Yukawa sector. And second thing we know is this is double Higgs production that agrees with our expectation is almost independent on alpha 1, but it depends on it's heavily dependent on the alpha 2. So that's the contact diagram. So okay, that's good. And also the same thing for alpha 3 in the 3 Higgs productions, for alpha 4 in 4 Higgs productions, and for alpha 5 in 5 Higgs productions. And then we can do this, like this one gives us alpha 2 smaller than 0.2 at 10 TeV, but smaller than 0.4 if you have 3 TeV machine. This one gives us the constraint of alpha 3. So we'll see how much better a 10 TeV machine is comparing to the 3 TeV machine in terms of this job. And then you'll see, okay, so alpha 4 and alpha 5, the constraint is around 1%. Just as a reminder, we didn't consider the misidentification of Z boson to Higgs, so it may be worse if we do more realistic simulations. And on the other side, if you believe the dimension 6 operator is the most dominant one for the BSM effect, and dimension 8 is highly surprised, we do one thing. We stay with this alpha, as I said, the linear relation between alpha 1 and alpha 2 and alpha 3. And for these two curves, those are also the kind of golden channels to measure alpha 1, because you can relate everything back to delta alpha 1. So that's kappa mu. And then that gives you, for di-Higgs production, a 3 TeV machine gives us like delta alpha 1 smaller than 0.3, or 10 TeV machine gives us delta alpha 1 smaller than 0.1. Or from this triple Higgs production, a 3 TeV machine gives us delta alpha 1 smaller than 0.7, but 10 TeV machine gives us delta alpha 1 is smaller than 5%. And then, of course, there are some other processes, as I showed. Here's the WW Higgs production at 3 TeV muon collider. This is the corresponding thing at the same thing at 10 TeV muon collider. And ZZ Higgs production, Z Higgs production. And you'll see in each plot, we plot this solid curve is before the cut. And this dashed curve is one of the cut, I think it's the invariant mass cut, and the dotted curve is after the angular cut. And you will see, okay, actually this WW Higgs is not that much sensitive to this new physics effect comparing to his two brothers. And also, again, all the signals are almost independent except for here, except for the Higgs production is kind of dependent on the beta 3 and Higgs 3 Higgs coupling. Otherwise, almost all of them are independent on this Higgs self-coupling. And the signal is much stronger at a 10 TeV machine. Then we can also have, as I said, if you have 2 vector bosons, it's equivalent to 1 Higgs. So if we go to higher multiplicities with those things to like 5D, so actually the sharpest thing, the best channel for pure vector boson production is 5 Higgs production at 10 TeV. So that also again is independent on the value of beta 3, so that we can focus in the Yukawa sector. And also, you see they depend on alpha 1 and alpha 2 simultaneously. So actually, if we want to do the constraint, we need to do a counterplot with alpha 1 and alpha 2. And here, I assumed this alpha 1 dependence for dimension 6 operator. So that we assume there's a one linear relation between the alpha 1 and alpha 2 following the dimension 6 smoothed way. So that's the dependence for that thing. And also we have even more processes in the table. So here, if we go to even higher multiplicity, we see besides alpha 1, alpha 2, there's also alpha 3. And we notice that actually those processes are not really helpful in constraining the kappa mu if we believe the dimension 6 smoothed. However, if you do think you want to keep in general to follow the Heft way, you say, okay, they are still helpful to constrain my parameter space. So you are forced to go to a parameter region where it's closer to the dimension 6 where. But however, in this way, we need to constrain alpha 1 to 3 together, so that if you do want to plot out the counterplot, is something the three-dimensional thing in the space. And that, as far as we can imagine, if you include even higher multiplicities with, for example, alpha 4 here, and then we need to do a counterplot in a 4-dimensional hyperspace. That's something too much complicated for us. So here is kind of a result from the multi-vector boson production, and also from the Higgs associated vector boson production, like WW Higgs, DD Higgs. And this one is a counterplot in the alpha 1, alpha 2 space. This one is counterplot also, this 3 TeV and 10 TeV. And this red, green, blue, those are just colors for different signal strengths for 2 sigma, 3 sigma, and 5 sigma. And please look at this dashed curve first, because in the dashed curve, I only included those processes that are dependent on alpha 1 and alpha 2. So that there's no other assumptions on what the alpha 3 should be. And then here is a straight line. Also here, the straight line is the smoothed dimension 6 smoothed line, so for which the alpha 1 and the alpha 2, they are linearly related. And then you can do something in that way. We do this. In the other way, you can also assume if alpha 3 is 0, if we go back, sorry, if we can go back, if we go back to here, we believe, if we do believe that like alpha 3 or alpha 4, alpha 5 are highly measured constraints in this multi-Higgs production channel, and if we do trust that, we can say, okay, what if the alpha 3 is almost 0? And then we can use, those processes to help to improve the counter in the alpha 1, alpha 2 space in the plane. And in that way, we have a delta alpha 1 smaller than 0.75, or alpha 2 smaller than 0.4 at 3 TeV machine with the 1 inverse echo bar luminosity. And also the same thing for the 10 TeV machine is delta alpha 1 smaller than 0.1, or the alpha 2 smaller than 0.1. And this blue number is the one that if you do assume, do trust is still the dimension 6 operator dominated, if you trust this line. So sorry, this one is just this cut point, this one and this one for the corresponding value of this delta alpha 1. And this one is, you see, here and here for a 95% confidence level. And what if the other way around? In here, as you say, those things, they are dependent on the alpha 1, alpha 2, alpha 3. What if we believe that alpha 1 is already well measured at high luminosity at FCTE or at whatever other machines, if this one is very well measured, and we can assume, what if alpha 1 equals to 1? And then actually you see this one breaks this relation I mentioned several times in the dimension 6 SMAFT, but it's still allowed in Heft framework. So we just, for the curiosity, pure curiosity, we show this plot in the alpha 2 and alpha 3 space. And also here is the bound from 3 Higgs productions on alpha 3 at 3 TeV. So this plot, this bound only gives us some constraint in the alpha 2 direction. And here is actually, if you do this assumption, it gives us kind of a small constraint, like, okay, alpha 2 should be smaller than 0.02, alpha 3 should also be smaller than 0.02. And that constraint is kind of comparable, a little bit weaker, but kind of, even stronger, maybe. Even stronger than the one in, we can see it in the multi-Higgs productions. However, I need to remind here, in doing this, we didn't make any assumption. In doing that, we assumed that the mu to single Higgs production is a standard model one. And that's where the dimension 6 SMAFT failed. And here's is my summary. So everyone knows that muon collider is super cool. It's an exciting high energy frontier. And also it gives us another chance for precision test for the standard model. But however, I have to emphasize, this is our first time to play with another flavor. I mean, this is our first time to play with the beam from the second generation. I remember there was a question asked at the muon collider workshop just I think last month. Oh, sorry, in May at Daisy. So there's an expert. I think he's the linear collider guy. He asked one question. So apart from your ability of going to high energy for the TeV machine, what is the other advantage of the muon collider over the electron positron collider? He said, assume if we have the plasma acceleration technology well, if we have the weak field acceleration technology well, we can assume one day if we can produce, like, we really build a 10 TeV linear collider. So what's the advantage? What makes the muon collider unique? So my naive understanding is this is something. You see that everything in the very beginning, what I said here, this one, if we do have a 10 TeV E plus E minus machine, we can do something similar than this. WW fusion, we can do that. This general picture, if we do have a 10 TeV E plus E minus machine, we can do that. And this one, if we have 10 TeV E plus E minus machine, we can do that. But however, what I said here, this thing, with the E plus E minus machine, of course we cannot do that. So I think this is something unique also for the muon collider. So that day I said, okay, sir, you cannot do the muon G minus 2 as well as we can do at muon collider. You cannot measure the muon Yukawa in this way as I do in muon collider. Maybe that's the answer. And also back to my report today, for my talk today. So if we do this measurement on the Higgs to muon interactions in this way in the production channel instead of the Higgs decay channel, we don't have to assume anything for the Higgs decay branching ratios or Higgs decay widths. And also this is kind of a direct probe on this mu to n Higgs vertex, because that's the contact term that you can do, and we cannot do that at other machines because we don't have the mu beam there. Perhaps one day they can say the other way around. They can produce a lot of Higgs from the other side to have Higgs collision to mu, but that is ridiculous. No one want to do that. So I think this is kind of unique channel. And also for the other processes, we need to at least constrain alpha 1 and alpha 2 together. And this is also a place that we can say this. I don't want to start a war, but it's rather a place you can say the SMAFT versus Heft, because in SMAFT there's different vertex are really related to each other, but in half they are just the free parameters. And at least we can say if something doesn't agree with the SMAFT, then it might be the linear, the linear representation is not really, it doesn't really work for the Higgs sector, or maybe there's a kind of a strong corrections from the dimension 8 or even higher dimensional operators. And the last comment is, from what I see, at least for this job, the signal strength is much better at a 10 TeV machine than rather than the 3 TeV1. Here we assume the 10 inverse echo bar for the luminosity at 10 TeV machine and 1 inverse echo bar for luminosity for 3 TeV. But however, the difference in the luminosities is not the game changer. It's rather that at 10 TeV machine you have something like this. At 10 TeV machine, the new physics effect is more enhanced by the energy comparing to what we see at 3 TeV machine. So that's what I have.
I wanted to ask you, if probably you didn't, but did you try to think which models you could probe with these measurements of alpha 1, alpha 2? I'm saying specifically because in the context of, as people say, probing SMAFT versus heft. If there is significant departures from the normal standard model effective theory, it means that there are new light particles. Okay, it means that there are new light degrees of freedom because your cutoff it becomes small. So have you tried to map, if you want, these results on models with extra X doublets, maybe light, but maybe I don't know, can be elusive from somewhere else? So what's the BSM impact, if you want, of this study that you envisage?
I mean, when doing that, I didn't think about what kind of model at that time. Maybe just want to show this how much we can go along this direction to see what the machine can do. But yes, I'm waiting to learn more on the model side.
Oh, I'm not 100% sure. I don't know. I haven't tried. I mean, of course, we'll have other effects. But...
We ended up with something. I don't want. Maybe Giuliano remembers, because we made up a model for the Yukawa of the electron. I'm sure it can work also for the Yukawa of the muon at that point. But let's see if either me or him remember the model.
If you have 10 Higgs bosons in the final state, which is a wonderful problem to have you given any thought to how you would identify them?
Pardon me, please.
You've talked about final states with 10 Higgs bosons in them. How do you propose to detect them?
Honestly, I haven't thought about that, but I mean, the thing I showed here is up to 10, and we knew we could not really go to 10, so we actually I mean, in the more realistic simulations, we stopped at 5 actually.
Well, let's take 5.
Yeah.
How do you identify them in an experiment? What are the challenges? What branching fractions do you have to pay?
I mean, if we follow the way, like we take the biggest branching fraction, the Higgs to BB bar decay, and then that's around like 50% already for each Higgs. And if you want to tag all the Higgs, it's just 1/2 to the fifth. And however, here is if it's a high energy machine, this some of the Higgs produced, it might be boosted so well. So it's not really, the BB bar is kind of fat jet. So that part I think is a bit challenging, but I didn't really look into like how we can do that for the detector side, because I think before reaching the detectors, you have a very high energy Higgs, and yeah, sure, you can decay, but you can also shower, like goes to some radiations. But in the very end, at detector side, you may not see the decay product of the Higgs, and maybe some kind of electroweak jet. So that part is not so clear to me. So that's something I think I need to ask people here.
So I think the model was something along the following line. You can put another doublet and you give it a VEV equal to 500 kVs. And you couple it to everything. So you may move the W mass, the Z mass, the top mass, everything by 500 kVs, which is undetectable for any mass you can think of, except that the electron mass would change by a factor of 2, maybe. And now if you allow me to do the same trick with the muon and do something else for the electron, because now I screw up the electron, I know. But at least for the electron being the lightest, there was a sort of proof of existence and not too shameful model, let's say. For the muon, indeed, it's not the same. But yeah, you can imagine solutions probably of this sort. Cancel a factor 100 in the electron, pay a fine at the fine-tuning police, and huh? No, this was in fact arising for the. Why do you want to do an FCC run at the Electron Yokawa?
Doesn't matter. If now you have the electron, that is fine.
Just asking the same question for the electron. Can you even write a model?
Change the model. In the sense that we don't have a probe, direct probe of the electron.
So far, no. Yeah, absolutely. Yes. But you still have to acknowledge that if there is a Higgs and another Higgs, that they conspire to cancel a factor 200 or 100, whatever it is, to give you the right mass of the muon and of the electron at the same time. Vabbè, so not really. Now, the other question probably related to this is exactly that. I think it's very instructive to look at the models that one could have to modify these relations, or at least to know from dimension 8, how big must be the contribution from dimension 8. In your alphas, you have also had subleading contributions.
You mean
alpha 1, you had a table a bit before.
You mean this one?
I don't know.
Wait, sorry.
Maybe, but you had expressions for alphas in a previous table where there were dimension 8 contributions appearing. Table. Before this, yeah, this one.
This one, yeah.
So at dimension 6, there is a relation between alpha 1, alpha 2, alpha 3.
Yes.
And that's a fact. Now, how big is the relation, the effect of dimension 8 that you are sensitive to? Let's say with your measurements, you are testing this relation to some precision.
Yes.
Which maybe corresponds to a suitably large dimension 8 effect, or maybe corresponds to an incredibly low lambda, let's say, for the dimension 8. That's another way of checking what kind of models.
Yes, exactly. So if we assume, we don't have to assume, there are some other UV complete models. I forgot those names, but if I think we even built some toy model, which is not really kind of serious. The new physics effect doesn't show up at dimension 6. So actually the leading order starts from dimension 8. So the thing what you can do is if we go here, we just need to replace this straight line by another line, with another slope for the other linear relations between the alpha 1, 2, 3, 4. But if you see a more general case, like you say, for example, if you say, okay, maybe the the dimension 8 is kind of comparable at same level to the dimension 6. It's more complicated. We cannot really do with one straight line. But in that way, I'm gonna start questioning. So if that happens between dimension 6 and dimension 8, you say that dimension 8 is not really power surprised that well. Does it mean the SMAP fails, or does it mean we are not
Dimension
parameterizing
6
that
is the
new
same
fails?
size of dimension 8 here. I think you can say SMEF is not a valid expansion here.
Mhm.
Wait a moment.
Yeah, I can't do it in my head. Sounds on alpha and alpha 2. Did you just, in SMEF, did you just calculate what the new physics scale was?
Which one?
Okay. The bounds on alpha you had at some point were in GV something.
I mean, this one.
Yeah, these 10 to the minus
This
9
one.
GVs. Well, somebody help me, but I think it's 30 TeV in the scale. But
Mhm.
Well, yes, there is a new power of the new register, right?
so it's what? 3 GV?
No, what I'm saying is that C,
Eh,
you should not take at face value the value lambda in that expression because in a reasonable model, you probably expect that L phi 6 to be not 1.
Uh-huh.
No, but this connects to the discussion about realistic models that we had before, no? If you don't want to tune terribly the mu you cover in your complete model, probably that C will be small.
Yes.
so indeed, I think it's at 10 TeV, you're sensitive to 30 TeV from this number, but you're saying you're applying an overall factor in front, which could be.
TeV is not the mass of the new particles that you have in your.
All right. No, fine. So you are probably bringing it to much below 10 TeV. That's what I wanted to say. Then again, you must have new physics directly accessible
Yeah.
at this machine if you're sensitive, if you buy this power counting where you put Yukawa everywhere.
So I believe this is something, even though we don't think about the model, is kind of guaranteed discovery. I mean, as long as you turn on the machine, I think you can see these constraints.
Fabio. Your code or
No.
any further comments or questions or models?
No, so if no more questions, I think it's time for me to ask questions, right?
Okay.
So I want to repeat the question I just mentioned from that linear collider guy. So what do you have in mind that multi-TeV muon collider can do, but only a multi-TeV muon collider can do, but a multi-TeV electron positron cannot do? Okay. But that's not the main reason we build such a machine, right? You don't build a muon collider for me.
Are you thinking 10 TeV electron collider? Are you?
What?
10 TeV electron collider. You're comparing 10 TeV electron collider?
Yeah, I'm comparing 10 TeV
with 10 TeV muon collider.
Yes.
Okay.
See. And also, yeah.
No, I just that's one thing. The other thing is that I don't know if it's connected to the question. There is not even an attempt of a plan for a plasma collider at E plus E minus at 10 TeV.
I know.
So
I know.
it would be great. And also it would be great if it could become 30, 40, in which case maybe the muon collider will not fall. We don't know what technology will do.
For sure.
But on the other hand, it's not a compelling objection in the sense that the plasma E plus E minus 10 TeV is today more a dream than the muon collider is.
I know. But that's not the physics question. The question if it's a very strong assumption, if you do have the two machines next to next, that they press the button, they run together, is there anything you can do only that?
Then there is in technology viewpoint, there is beam Strahlung that is needed when you have linear colliders because they have to have a very, very small beam spot, which makes collective effect, that make that one beam make that the electrons or positron in the other beam lose energy. And so if that has to continue with the scaling that there is from clique, so going to higher energy, this will make that you lose a huge amount of luminosity and you get a lot of soft photons of lower energy electron. So the collider stops becoming very clean. because of this effect called Beam-Strahlung, and also you lose luminosity at the higher energy.
Asking was telling me that you can get hard photon from that effect. You can optimize to get hard photon.
Why? Then you have gamma. Then either you speak at the gamma collider at 10 TeV, which is again you need direct plus E minus at maybe 100 for getting gamma 10 TeV. I don't know if you change the collider. Yes, a gamma collider would be very clean and nice. No, Michael is saying you can stimulate the emission of hard photons, and so you end up with a sort of gamma collider. So if you speak at gamma collider at 10 TeV with no much background from the beam, because of so I don't know what he's speaking about. It can be something interesting, but we should be first see what they're speaking about.
This cannot be done with muon. You cannot efficiently convert your 5 TeV muons into 5 TeV photons. Or
not even close to 5 TeV. I mean, no, but not even at the electron. You cannot emit, you cannot change. I mean, the emission is always going to be emission soft, right? You cannot give all the energy to a photon. I mean, if Michael was there, maybe he would clarify, but I think it's obvious because the mass. So, boo. Yeah.
that's something you can do.
Capito, but why you want to do that? I'm saying you want to build another collider, which is gamma collider. That will go through electrons, fine. And you can do a gamma collider at some energy, okay? Some energy which will not be the 10 TeV today. But that would be an interesting question. The physics case of a gamma. But then, so the higher muon mass makes this unfavorable, no? The emission is less. So the physics case of a gamma collider of X TeV would be interesting to see and compare with the muon collider, I guess.
And may I ask my last question? It's kind of a, I'm just revisiting the question I was asked by Chris, like, what's the current status of detecting the Higgs at muon collider TeV?
What do you mean? What's the current status?
If assume I have a Higgs aside, I assume I want to produce 2 or 3 or 5 Higgs.
So I think something you said is interesting. So if those Higgs were to be boosted, right? So I think it would be somewhat easier in the sense that, okay, you would need to do some larger jet dagger to find the Higgs, but at least you get rid of the combinatorics, right?
So you say the highly boosted Higgs actually makes it easier, not harder.
If you have 5 Higgs, right?
But if 1 Higgs,
if you have 1 Higgs, okay, you do BB bar and
it's still boosted, and is that something bad or something?
In that case, I don't think you need it to be boosted, right? But if you have 5 of them, there is also a huge problem with correctly assigning the particles that they decay to, right? And if they're boosted, then you get rid of the problem.
I see. But how much do we worry about the misidentification from the Day boson to be the Higgs boson?
So I think today, you know well, right? These invariant mass plots that have been studied. I think we have good reason to believe that this is not the final performance. We think we can get a final performance which is similar to what you see, I don't know, at a click 3 TeV, where you could even tell apart at 2, 3 sigma W's from Z's. We don't have the tools to do it yet.
I see.
But there is a priori no reason to believe we can't do it with.
I don't believe we cannot do it, but I just want to know that the most updated status.
The most up-to-date status is a little bit better than these plots that you know very well.
I see.
And they got better during the workshop.
First, I hope that this possibility of a 10 TeV electron collider and 10 TeV muon collider will be presented to us very soon. And then we can try to make our choices based on availability, cost, reliability, and all of that. One difference between the two, from the point of view of experiments, is that in a circular machine, it's very graceful to have multiple experiments. And in a linear collider, it's almost a fiction to talk about having more than one detector. Now, that may or may not be a decisive choice, but it is certainly a difference.
I think we can transition to discussion in the context of getting coffee at the machine or wherever you like. And thank Yang again.